I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Expedera with Sharad Chole. I'm going to talk today about application-optimized processors. Sharad, what is an application-optimized processor and how does it differ from what we've been using in the past?
We always been used to a notion of a general purpose computing, and so we have things like CPU or GPU, where general purpose computing is a focus of like enabling application that you have a programming paradigm and you are writing code in that programming paradigm. It might be C, Java, CUDA, any of such examples, and that applications write programs and they interface with the device using the compiled binary from that program. The application optimized neural network processor is taking a step in a slightly different direction, where instead of writing code or writing application in a certain language, we are actually executing a neural networks. And these neural networks are defined in a standard format, for example, ONNX or TF-Lite or PyTorch. So there are standard format that these neural networks are defined in, and we're taking those neural networks and executing them on top of the NPU with the consideration of what the application requirements are. Application requirements can be latency, they can be bandwidth, they can be power, or even the area budget that is required to enable the specific throughput of the application.
Where are you finding the most uptake of this? Is it in the data center? Is it in the edge? And the edge has
So,
data centers as well.
I would say data center primary drivers have been towards more general purpose computing, but given the workload that AI has actually enabled, like looking at LLMs, there has been a significant amount of research in even in the data center NPUs. But for us, the uh, application optimized NPU has become a very like fundamental part of edge devices, like especially sensor data and processing sensor data in real time, uh, in a low power where the human interaction can be enabled or even the device control can be enabled. And that has been a key differentiator for the edge devices where next generation of applications can be enabled.
Let's take a closer look.
Yeah, sure.
Sharad, what are we looking at?
So at the top, we are looking at a general definition of a neural network, and the way we are representing this is by representing the output of a layer as a tensor. Typically, a tensor is an n-dimensional array, where it can be two-dimensional, which can look like just a matrix. If it's a three-dimensional, it looks like an image or a volume. And if it's a four or more dimension, it's we have to imagine it, but it's basically a multi-dimensional volume or multi-dimensional array. That's what you can think of. Because we cannot draw more than three dimensions here, we just like represent all the tensors as three dimensions in this picture. But a tensor definition is independent of that. So a neural network can be represented as a graph of n-dimensional tensor. And this is a very simple example where you see output of four different layers, and these four different layers are basically connected from one layer to the next, to the next, to the next, and that's all.
And really what you're doing is you're partitioning a problem into various different pieces, right?
Yes. So what we are trying to do is to be able to optimize, to be able to process this neural network in more efficient fashion. We have to get away from definition of what neural networks are, right? So neural network gives us a graph definition, and if you're just depending on the graph definition, we are limited to only a layer-wise processing. So we can only do this layer followed by next layer, followed by next, followed by next. But this has its own limitation. So what happens is, if the neural network is too deep, then we are processing a significant amount of big layers, and we are maintaining the data going from one layer to the next layer. As well as we increase the resolution, the input resolution, the tensor sizes that we need to keep around dramatically increases. And that's where we need to actually go in and understand the fine-grained dependency between the neural networks. And that's what this step is.
What you're heading towards is a sort of a fundamental trade-off in computing, which says that in order to get more accurate results faster, you need to really have a lot more compute elements, right? How do you balance that?
So this is a really interesting question. When we are looking at GPU, we typically try to accelerate a very large problem on GPU. That's basically a way to get more efficiency or more trade-off. But what we notice is like very early is that if you are going in that direction, then we are managing too much of a temporary data to be active or alive and doing that processing. And this is not the right approach for the edge devices, because edge devices are very sensitive towards the memory as well as bandwidth. If we have a huge amount of data that we need to manage, we need to either store the data or we need to actually access it through the DDR, which is going to be very costly in terms of power and cost. So what we do is instead of like processing the neural network as layer by layer, we take a neural network layer and break it into smaller fragments.
What are these little blocks that you've broken it into?
So these blocks are basically taking a neural network output layers and breaking into a contiguous set of fragments of the tensor, and these are called packets. So packet is a self-consisting a command which has notion of all its metadata. For example, if it's a convolution, it knows what kind of convolution layer it is, what strides it needs to do, what padding it needs to happen. Also, what part of the output fragment that this packet belongs to. So it knows where the starting point of in each dimension is, where the end point in each dimension is. And the reason we call it a packet is the scheduling primitives for these small fragments actually correlate to how we schedule packets in networking domain. The scheduling of these packets basically gives us more freedom of how do we want to optimize these neural networks when we deploy them on the edge NPUs.
And the whole goal here is that you don't leave any Mac element or any compute element idle for any length of time, right?
Yeah, that's a really good point. So what we are trying to do here is to be able to process these packets out of order. So what we can do is based on a dependency. So instead of like having this neural network graph, we have a fine-grained dependency analysis of these packets. And based on the dependency, we can say that, okay, once this packet is being executed, this packet has all the data that is needed for execution. And once these 4 packets are executed, these packets has all the data that is needed for execution. So we can actually execute these packets completely out of order based on the dependency analysis of the packet graph. And using that, we can parallelize different packets. If this packet is running on one engine versus this packet is running on another engine, we can actually parallelize the execution of different packets on different engines.
So what you're doing is basically processing asynchronously, right?
If you are looking at this from a layer-wise computing perspective, yes, we are processing it asynchronously, out of order. We are also prefetching the data, so we are actually like utilizing a lot of techniques that are being used in the CPU world for instruction management and instruction fetching. But here, the workload is not dynamic; it's known in advance, which is static, and which makes the compilation process quite ahead of time as well as very efficient.
One of the challenges when you parallelize any operation is that you have to bring all that data back together in a consistent form. When you do it out of order, does it become more difficult?
When we are doing things out of order, the biggest challenge is the memory subsystem. So how do we get the data back to where it is needed, and how do we manage uh, these data access parallelly with different engines? So we had to design our hardware in a way where we can do a context switch without facing a penalty. So we'll go to the hardware, but the whole idea of like switching between one packet to another packet is basically the same as switching between one layer to the next layer. Because all the data that is required to process the packet, all the constants, all the quantization information, all the attributes, uh, they need to be context switched. And so for the for the other hardwares, this context switch happens at a layer level, which can be very big at time scale. But when we are designing our NPU, this context switch happens at packet level, where only a small fragment of computation finishes, and we have to context switch to the next new packet. And for that, we have to make sure that the context switch is completely efficient, that we do not lose any cycle within our hardware to be able to context switch.
Basically, you're taking the advantage of what you do in software and really building it into the hardware, right?
Yes. So we actually design our hardware as a deeply pipelined architecture, and you can actually see that this block diagram here, which consists of 5 different building blocks families. And each building block family has its own capabilities in terms of what precision it can support, what computation it can support, um, what functionality it does support. So this is basically a 4 by 4 grid that you can see of MMP array, or this is the matrix processor in the blue. And the green ones that you see here are basically a vector scalar processors. And finally, we have a memory here, which is again aligned with the computational elements. The goal of having the memory here, which is aligned with the computational elements, is to make sure that the data is always traveling in a straight line. So we take care of the physical design consideration, which can guarantee that the power is minimized, as well as the latency that, or the frequency that you can achieve is higher. There's also a notion of SSP here, which is the sequencer and scheduler block. And this is basically the control where all the packets reside and the packets are executed from. Now, going back to the DP pipeline execution. So this SSP is the responsible for taking in the packets here defined here and converting into a cycle level instructions. So the SSP is creating cycle level instructions, and these instructions are timed so that all the instructions can be sent to different blocks simultaneously, and they can execute in parallel. Also, the instructions travel through this system in a deeply pipeline fashion, and with that, the data within the system also travels in a deeply pipeline fashion, which means that when we do a context switch between one packet to the next packet, the instruction already has this notion that, okay, we are going to do the context switch and we need to load this registers, or we need to start processing these data other than that data. And that can be completely managed throughout the system without having a penalty.
When engineers are working with this, where do they typically go wrong? And what do they have to watch out for?
Yeah, it's very easy to design a system to which the system which can take in a definition of a very big workload. Like for example, you have a workload which can do 10 milliseconds, and you want to do just a matrix multiplication for 10 milliseconds. It's very easy to design that system because you have one instruction that's going to come in, that's going to give you a data, that's going to give you the number of like the tensor dimensions, and you can just like create a sequencer for that. It becomes much harder when the granularity of this execution becomes maybe tens of cycles. So what we are talking about is tens of nanoseconds here. And now we have to worry about, okay, are we over designing the system? Are we taking too much cost to manage the context switch to be penalty free? And that's the trade-off that we have made in this architecture. What you see here is something that is still give you the best performance that you can get, but without having an over design uh, to optimize the context switch.
What other knobs can you turn here to make this more efficient?
So in terms of area, what we see is memories are the predominant portion of the quantized NPU. Like if you are executing in terms of int 8 or int 4, then the memory is taking significant amount of more area than this computational block. And these memories might be, this area might be prohibitive if we are just using these memories for the NPU. So one of the knobs that we provide is we can actually have this memory shared with the system, and we can statically carry out the memory to like different system and expose ports to the system so that like the application processor or external system can access the memory as if it's a common shared memory. We also have ability to change the frequency. So for example, by reducing the frequency, you can do lesser amount of uh, power. And this more like, I think everybody in the edge industry know that this is more about the frequency and voltage scaling that we need to design. So when we define our NPU, or when we actually take into consideration physical design, we are actually taking into consideration how this frequency and voltage scaling can be applied, so that if you're not really want that much performance, you can increase the power efficiency of the system.
And you can turn some of these processing elements off and on as needed, right?
Yeah. So I see NPU as being in three different stages, right? Like the one stage is when the NPU is not being used at all, and in that case, the entire NPU can be turned off completely. The another stage is NPU is only partially active, and in this case, what we make sure is the entire design is completely clock gated and gives you the best possible static power or idle power when the NPU is not being utilized. And finally, the third stage is fully active. We always want, when applications are running, that we are utilizing the complete capacity of the NPU. Otherwise, otherwise the NPU will be over-designed for your application. So we always make sure that we have defined NPU in terms of bandwidth and in terms of power to be fully utilized.
So really, when you design this, you really need to understand what your end market is, what the application is, and what your use case is, right, to really optimize this.
When our customers actually come to us, they're basically coming to us with a set of neural network workloads. So a workload is defined as, okay, you have this neural network that you want to run. They can be that set can be running as pipeline fashion, that like neural networks needs to be executed in pipeline fashion, or they can be running in parallel fashion, that multiple neural networks can be running in parallel. And then there is a constraint over what target throughput or what latency we need to achieve for each of the neural network in the workload. And what is the system constraints are there? For example, bandwidth. How much bandwidth are we allowed to be allocated to the NPU? Peak bandwidth. What is the maximum power that is need to fit under? What is the area budget that the NPU needs to fit under? And with this, we have a complete picture of what an application constraint is. And now the goal that we have as maybe someone who is helping SOC architect is to come up with different solutions and different trade-off analysis that our customers can make more intelligent decisions on uh, how they can trade off the application, how they can trade off the accuracy versus power versus performance and things like that.
Sharad Chole, thanks for a great explanation.
Thank you.